Okay, so I just draw two potential models. So the left side is for the hydrogen atom, and the right side is for tungsten metal. Tungsten metal. Okay. So from the quantum chemistry theory, for hydrogen atom, right? There are different orbitals with a principal number, quantum number n equals to 1, 2, 3, 4, and all the way to n equals infinite. Right. And for the n equals to 1 principal quantum number, the subquantum is there 1s. Okay, n equals 1 equals 1, so there is the 1s orbital, 1s, and n equals 2. There are 2s and 2p, other orbitals. And for each hydrogen atom, there's one electron, just one electron for hydrogen atom. So if you want to ionize hydrogen atom, right? So the hydrogen atoms change to hydrogen or cation and a free electron. So you need to provide energy to hydrogen atom to bring these electrons, right, all the way to this level, n equal to infinite. Okay. And for hydrogen, this energy equals to ionization energy. .6 electron volt. You need to provide an energy equivalent to 13.6 electron volt to ionize an hydrogen atom to an hydrogen cation, or a proton and a free electron. Okay, this is from the quantum chemistry. And for tungsten metal, right? A piece of tungsten metal, there are, plenty, a lot of tungsten atoms, right? They are stacked in ordered way and closely packed. So we cannot use this quantum model to describe the energy of electrons inside the tungsten. So in other way, one must use the solid state physics to explain the energy of electron in tungsten metal. Okay, so here is the Fermi level, EF Fermi level. Okay, and metallic materials are conductor because they have a partially filled band structure. Okay, so the maximum energy of the electron. Okay, so they are electrons with different energies. So again, the vertical axis is the potential energy, or the energy of the electron. Okay, so inside of tungsten metal, so the left side is the tungsten metal. Left side is tungsten metal. The right side is in vacuum. The surface of tungsten metal and vacuum. So inside the tungsten metal, there are plenty of valence electron. Okay. And the maximum energy of this valence electron is at the Fermi level. Okay. So here is the barrier. If you can provide an energy, right, equal to the difference of the potential between the vacuum level and the Fermi level, you can let the electron escape. Right, the electron escape to vacuum level. And this energy difference is the work function over here, the work function. This energy difference is work function. And for general metals, their work function is close to 4 electron volt. Little bit higher or little bit smaller work function. Right? So for example, the work function for tungsten is around 4 point something, maybe close to 4.5 electron volts. So if you compare this band or potential model of the tungsten metal and this model for hydrogen atoms, and tungsten, right? For the hydrogen atoms, if you ionize the hydrogen atoms, you need to bring the electrons from 1s orbital to n equal infinite. And this electron become free electron. They will escape from the attractive force of the proton. So this one become free. And in this part, when the electrons overcome the barrier of work function, they can emit out. So again, this is also the free electron. Escape from the material, from the solid surface. Okay. So the energy of free electrons in these two models are equal. You cannot distinguish whether this electron coming from tungsten or coming from hydrogen or other cases. So here is the same standard of the potential, same standard. Vacuum level, also this part can also be named the vacuum level. Okay. So for hydrogen, if you want to ionize hydrogen, you need an energy of 13.6 volt. And for the tungsten metal, if you want to get the electron emitting out from tungsten surface, you only need an energy of 4.5 electron volt. 4.5 electron volts. Okay. So let's look back to this figure. The horizontal axis, the lower axis, shows the wavelength of light. And the upper numbers shows energy of photon. So from here, 2 electron volts, 3 electron volts, 4 electron volts. So based on this figure, you can find out if you use a light beam with photon energy of 4.5 electron volt, you can get secondary electron emission or photon emission from metal surface easily. Depends on the work function of the metal. right? Aluminum and lithium has low work function, and gold has, and platinum have high work function. High work function. Okay. So if you want to get a photon emission, you must select the light with certain wavelengths. Okay. So if the energy of the light is too small, you cannot get secondary. You cannot get photon emission from gold surface. If you use an energy of light of around 4 electron volts, you cannot get secondary. You cannot get photon emission from gold, but you can get photon emission from aluminum, because aluminum has a lower work function compared to the gold. Okay. Okay. So for the photon emission, the photoelectrical yield gamma P is about 10 to minus 4 to 10 to minus 3 in a glow discharge. And only visible, only UV light contribute to the photon emission for the material with high work function. And part of the metals can get photon emission by visible light irradiation. But the photoelectrical yield is still very small, 10 to minus 4 to 10 to minus 3, right? And it's, the neutral bombardment also give very small yield of secondary electron. So only in this part, electron bombardment and ion bombardment can give significant secondary electron emission, okay, from the solid surface. So in Chapman's book, this chapter further discuss the ways to generate plasma. So the important part is in the cathode region. In cathode region, so Chapman gives an example. So in a DC discharge system, if you apply a power supply and give a current density of 0.3 milliamp per centimeter square, okay, a current density of such current density, and for such current density, you need to generate electron and ion pairs, or you need the flux of electrons and ion pairs with around 1.9 times 10 to 15 per centimeter square per second. So this is the flux of ions and electrons, right, flowing between cathode and anode. Right, they flow in a reverse opposite direction. Okay. So based on this, the example, one need an ion and electron pair production rate of at least 3.8 times 10 to 15 per second. So this is the example. So Chapman analyzed the models proposed by Townsend previously, right? So in the cathode region, this is in the cathode region. So left side is cathode, And the dots, the region of dots here is the edge of negative glow. So this part is the cathode region, and the length between cathode surface and the edge of negative glow is the cathode layer thickness. Cathode layer thickness. In previous chapter, we use a D sub C, right, to describe this region, the cathode layer thickness. Cathode layer thickness. Okay. So the arrow is the cathode layer thickness. So from the other measurement, people have already known in a DC discharge system, the most potential drop fall in the cathode layer, cathode region. So here is a potential drop from a plasma to the cathode surface. And plasma has a potential a little bit higher than the ground potential. And cathode surface has a negative potential. Negative potential. So in this region, there is an electrical field. Electrical field, right? So the electrical field pointing from the right to the left side. So this electrical field will accelerate ions. So when the ion come to the surface of cathode, the ions might have an energy of few hundred volts in a normal plasma, normal glow discharge system. Okay. So when the ion collide with cathode surface, these ions can cause the emission of secondary electron. Right? The emission of secondary electron by ion bombardment. Emission of secondary electron by ion bombardment. And this ratio is gamma sub I, secondary emission for ion bombardment. So if the ion flux, right, the unit is milliamp per centimeter per second, the ion flux. Okay. So if the ion flux is J sub I, so this is the J sub I, and then the secondary electron coming out from the cathode surface, the flux of the secondary electron equals to gamma times J sub I. Okay, and this process will give the electrons coming out, and the electrons travel across the cathode layer. Electrons can gain energy, and in Townsend's model, there are collisional process in cathode layer. But later on, you can find out the Chapman didn't agree this model. So Chapman assumed there's no, or other scientists, they modify the theory. So they assume there's no collision. There's no collisional process in cathode layer. But if we just follow Townsend's model, and we assume there are collisional process in the cathode zone. So when electrons travel, right, toward the negative glow, they gain energy. And when the electron collide with a gas atom, they will cause electron impact ionization. So the gas atom becomes a cation and an electron and ion pair. So this shows the electrons and ion pair. So this arrow shows the direction of electron after the electron impact ionization. Electron impact ionization, okay. So after the electron impact ionization, one can get a pair of electron and ion. And the electron will keep, I'm sorry, wrong direction. This is the ion. This is the electron. Electron should move this way, electron. Okay. And this is also the electron coming out. So for the one electron coming out from cathode surface, when it collides with a gas atom and form an electron and ion pair, and also the primary electron lost energy, but still stay inside the cathode. So there are two electrons here after the collisional process. One is the secondary electron by ionization process. The other one is the primary electron, but with less energy. Okay. So when the electron, the newly generated electron and the original electron keep traveling toward the anode, they also got energy from electrical field and might induce another collisional process so that one can get more and more electrons, ion pairs. Okay. So we have already known this story in a previous chapter. So when the electron travel from cathode surface toward the edge of negative glow, the number of electrons and number of ions increase, or the density of ion and electron increase, and they can follow. The model give us this equation from the last chapter. We also have already seen this equation. Right? In this place, right, the electron density equals to the, at the position of X, equals to the electron density at the surface of cathode times an exponential term. But in this chapter, Chapman used the NQX. N is the density of electron, Q is the cross-section. Right. The cross-section of the collisional process, and X is the distance to describe the number of the ionizing collisions, the number of electron and the ion pairs inside the cathode layer. Okay, and the newly generated electron and ion pairs equals to the exponential NQL minus 1. So at the edge of negative glow, we can calculate the number of newly increased electrons. So it should be equal to this number minus 1 if at the beginning there's one electron coming out from cathode surface. Okay, this equation. And the newly generated electron and ion pair, right? Ion will again travel to the surface of the cathode, to the surface of cathode, and then generate secondary electron. Secondary electron. Okay. So before the first electron disappear in the negative glow, the surface of the cathode can supply this number of electrons. So before one electron disappear in the negative glow, the surface of the cathode can provide this number, right? This number of the electrons. Okay. So from this this model, we need to know this number. So we need a condition so that this equation, the gamma times exponential NQL minus 1 equals to 1 or larger than 1. Larger than 1, and then equal or larger than 1, and then you can keep stable plasma discharge. Before the electron loss to negative glow, you can get the newly supplied electrons from the cathode. So Chapman analyzed this example, right? This example, if you want to keep a glow discharge with a current density of such value, you need electron and ion flux about 1.9 times 10 to 15 per centimeter per second. Okay, or you need the ion electron pair production rate of at least 3.8 times 10 to 5 per second. Okay, so in Chapman's book, he gives us these calculations. So for example, if the cross-section of the electron impact ionization in argon gas, in argon plasma is 2.9 times 10 to minus 16 centimeter. Okay, and electron energy is 100 electron volts. Okay, okay, so that you can get the exponential NQL. Q is the cross section, right? And the cathode layer thickness. Let us assume the cathode layer thickness is about 1.3 centimeter. So you got the QL, and you got the N in a previous place. Got the N. Yeah. Oh, N is here. N is the density of the plasma, around 2.1 times 10 to minus, times 10 to 15 per cube centimeter. So you got the exponential NQL equals 2.2. And the equation gamma times, the important part is this equation gamma times exponential NQL minus 1. Right? Similar to the tungsten's the analysis. So the NQL minus 1 is 2.2 minus 1. And gamma in this place is about 0.2, 0.2, right? For most gamma. Right. Gamma. the secondary electron emission from ion bombardment, right, from here is about 0.2. So you can use this value to estimate the number here. Okay, so you can get 0.24. So from this equation, you only got 0.24 newly generated electron and ion pairs. So this value is smaller than 1. Smaller than 1. So just by the processes Chapman mentioned, the electron coming out from cathode surface and ionization gas inside cathode layer, right? By just using these two effects to estimate the newly generated ion and electron pair, the number is equal to 0.24. This value is smaller than 1. So when you lost one electron to negative glow, the cathode layer only can supply 0.24 newly generated electron and ion pair. Okay, so the electron density and ion density will become smaller and smaller, and eventually plasma will extinguish based on this calculation. Okay. And if you consider another process, okay, when ion collide with neutral atoms to form the electron and ion pairs, we can approximately get the newly generated electron and ion pairs equals to 2.15. And if you add these two values, you just got 0.39. So again, the sum of these two values, is smaller than 1. So based on this model, so this model is adopted from Townsend's analysis, right? But Chapman used an example and then find out in the cathode layer, inside the cathode layer, even you consider all the possible reactions, you still cannot get enough newly generated electron and ion pairs. Okay. So Chapman, in Chapman's book, in this chapter, suggests major ionization sources may come from negative glow. So actually, in the cathode layer, inside the cathode layer, the collisional process cannot provide enough electron and ion pairs. So he proposed another model. So actually, it's Davis and Houston. They provide another model. So in this model, the negative glow is important. So there are plenty of the ions and electrons in negative glow. So when the cations travel across the edge of the negative glow, they can collide with gas atoms. And then their charge can exchange. Okay. So the most important part is cations in negative glow. Okay. And then later on, the cation bombard the surface of the cathode. Okay. So there is little or no ionization process in the cathode layer or in the cathode sheath. In cathode sheath, the dominant collisional process is from the charge exchange between cathode ions from negative glow and the gas atoms in the cathode layer. In cathode layer, okay. So negative glow is required for a glow discharge from this analysis. Okay. Okay. So far, any questions? Okay. So in this chapter, in Chapman's book, he used the example to prove that there's little or no collisional process in the cathode layer. In cathode layer, okay. So most cathode ions are supplied from negative glow. Negative glow. So those cathode ions and then when they travel toward the cathode surface, they can undergo this collisional process and generate secondary electron. Okay. Okay, and there are other collisional processes in the cathode region and in the anode region. Okay, so some of the electrons coming out from the cathode might possess very high energy, and when they travel across the cathode layer, okay, and the maximum energy of the electrons equivalent to the voltage drop or the potential drop in the cathode layer, in the cathode sheath. So if you use the DC power supply to provide 600 volts of the potential difference, the cathode fault will be little bit larger than 600 volts, right? It is 600 volts plus plasma potential. Usually the plasma potential is larger than ground potential, higher than ground potential. So you might get a cathode fault of 620 volts, okay? So this is the maximum energy electrons can get from the cathode sheath, okay? And so the electrons, when they travel across the cathode layer, there are limited collisional process, or we can consider there's no collisional process. So the energy of the electron will keep increasing if they travel across this cathode layer region, because the electrical field will accelerate electrons. So if you pick up an X value here, a cross section, right? You pick up a cross section here. So when the electron pass this cross section, and if you can measure the energy or velocity of the electron, you can find out the energy of the electron should be the same. And if you make a cross section at this place and measure the energy of electrons again, you can find out the electron energy will increase. Okay, but at a fixed distance from the cathode surface, you can always get monoenergetic electrons. monoenergetic electrons, okay, because they are accelerated so that velocity will increase when they travel for a longer distance. The velocity will become larger, okay. Okay, okay, and some fast electron might enter the globe directly, and this fast electron collide with gas atom and generate the electron and ion pair, generate electron and ion pairs, okay? And if there are multiple collisional process, after all, you can find out the electron energy will eventually, the distribution will follow the Maxwellian distribution, eventually, after multiple collisional process. But some high energy electrons escape from the cathode layer region, might travel all the way to the anode surface. So small amount of the fast electrons. Okay. And here it's about the anode region. Anode region. So there's a thin, very thin anode sheath near the anode surface. And because the sheath is very thin, so they are eventually or essentially collisionless, okay? No collisional process inside the anode sheath because the sheath is too thin, okay? And the ion energy, after the ion enters the anode sheath, they might get energy about kT over E. So this energy is originated from the potential difference between plasma and the ground anode. So actually, this part equals to the plasma potential. Plasma potential, right? So so here is the anode sheath. And the potential difference between plasma and the anode surface. And usually the anode surface is grounded. So the potential difference is plasma potential. Plasma potential. So the potential is around 10 to 15 electron volts, right? Usually in a general plasma system. Okay. And the anode surface will be bombarded by these ions because they are accelerated by the sheath voltage, right? About 10 to 15 electron volts. So they can still bombarded by the ions. And also the fast electrons travel all the way from cathode to the anode, right? So this electron will also collide or bombard the anode surface. And the photons inside the plasma irradiate the anode surface. So these particles will also generate secondary electron emission from anode surface. So anode surface also emit electron by ion bombardment, by electron bombardment, and by the photon emission. Okay. Okay. Yeah. Okay. And in the last part, this sentence said, because the anode collect electrons, right? In a complete circuit, the the electron coming out from cathode will collected by the anode. So when the electron collide with the anode, even this electron has slow velocity or low energy, when they collide with the anode surface, they will still cause the secondary electron emission. And the secondary electron emission yield is delta. 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 Okay. So even though the electron energy might be very small, the secondary electron yield by electron bombardment usually is higher than the secondary electron emission by ion bombardment, right? By ion bombardment, even though the ion energy can be as high as few hundred volts, the secondary electron emission for ion bombardment is less than 1. Less than 1. Here, 0.24, 0.25. But for the electron bombardment on the anode surface, even the incident electron energy is small, you can still get a secondary emission ratios a little bit higher than the secondary emission by ion bombardment. Yeah, here. So the last sentence let us know that this phenomena. Okay. Yeah, I think it is all about today's class. Do you have any